Yes, I apologize that I made you wait, but my brother had made a very exciting announcement. He said he's very interested in infinity and he needs my help. So I'm so happy. My brother wants to learn about infinity. Then what he does, he drives me early in the morning from 8 o'clock somewhere far outstate, parks the car. Apparently he bought an Infinity i30 1997 junk for $200. And then, why did I have to come is to drive the other car back. So that was my day. Of course, the story is true almost entirely. Which means it's true except on countably many points. So, so where did we stop? Cauchy-Schwarz. Did you review dot products, my darlings? Yes? I checked, I've seen that you haven't opened the video. So I hope that at least you opened the notes for Calc 3 where I just describe what dot products are, or that you read them somewhere else, that you know what dot products are supposed to do. So we have established Cauchy-Schwarz inequality last time, and the inequality states something that is very familiar. In essence, it says that the work is always less than or equal to the product of the magnitude of the force times the magnitude of the distance. That's the physical statement of Cauchy-Schwarz. But if you use higher dimensional spaces, you might wonder if angle is a viable notion, so you might have a more difficult proof. And in more advanced settings, you can then again generalize this proof. So the statement last time, Cauchy-Schwarz, and what it says is that given x and y belonging to Rn, and for those of you that bothered, you can see that it really x and y, they can belong in a much more general space, namely in L2, little L2. That means that it could be infinite dimensional but square summable. We know that the inner product of x times y, which is simply the summation of xk times yk, that's the dot product, and the summation goes either from k equal 1 to n or k equal 1 to infinity. This is less than or equal to the summation where I take each coordinate under absolute value. This in turn less than or equal to the product of the norms. So that's where we need square summability. So in terms of infinite series, that means if you take any sequence that's square summable and you do the dot product or inner product operation with another sequence that's square summable, it's going to be absolutely convergent, and the size of that series is less than the product of the square summable sequences. So that's Cauchy-Schwarz. We need this inequality to prove Minkowski's inequality. So then we have this theorem. Minkowski's inequality. And what this theorem states is that given x and y in Rn, again, better think of it as in L2, that's more general. We can say that the sum of x plus y under the 2 norm satisfies the triangle inequality. Okay, so notice I use the word 2 norm. Now, norm means, of course, it has to satisfy this triangle inequality, but we don't know that this 2 norm is a norm until we have this inequality. So proof. All you have to do is just notice that if I take x plus y and I square this norm, I just have the inner product of x plus y with x plus y. And then by using the properties of the inner product, I will see that this will be equal to the magnitude of x squared plus twice the inner product of x and y plus the magnitude of y squared. So I hope you review dot product and this is obvious to you, right? This follows again from, this is the dot product and the properties that I used here follow from here. So what can I see? By Cauchy-Schwarz, by Cauchy-Schwarz, or before Cauchy-Schwarz, I can just take the dot product and I can take its absolute value. So this is less than or equal to x, magnitude of x squared, plus twice the absolute value of, I should say absolute value. Absolute value of the inner product plus magnitude of y squared. And now here by Cauchy-Schwarz, I simply notice that this is less than or equal to the product of the norms of x and y. But then you look at this expression, this is your regular square operation. So this is less than or equal to so what do we have? We have that the square of the norm of x plus y is less than or equal to the sum of the norms squared. So from there, upon taking square roots, the inequality follows. Okay? Done. So this is the hardest step in showing that this usual Euclidean norm works as a norm. Indeed, it is a norm. It satisfies this triangle inequality. And then we have several observations that we want to extend the 2 to the p norm. So the observation that I first want to make is for p bigger than 1 and less than infinity, we have that if a and b are numbers bigger than or equal to 0, then if I take a plus b and raise it to the power p, this will be less than or equal to maximum of, to twice the maximum of A and B raised to the power of P, which is less than or equal to 2 to the power of P and maximum of AB to the power P. Now the maximum of A and B is either A or B. Regardless, this is less than or equal to 2 times P, parentheses A to the power of P plus B to the power of P. Do you agree? Because if the maximum was A, then this is equivalent to taking A to the P. If the maximum is B, it's B to the P. And of course, A to the P plus B to the P is bigger than this number, right? Because this is either A to the P or B to the P. The sum is bigger since they are positive. So this observation tells us the following. So that the conclusion from here is, and again, if you don't feel comfortable with P spaces, it's okay. Don't have to understand it unless you're a graduate student. So if you take X and Y and they are elements of L sub P, what does it mean that X and Y are elements of L sub P? It means that X and Y are both infinite sequences and they are P summable. It means that if I take each coordinate, each term of the sequence and raise it to the absolute value and then to the power P, and I add it together, it will be a finite number. Make sense? So an example what X could be is, for instance, the harmonic sequence for any P bigger than I would say bigger than 1, right? Well, that's good. But if P is bigger than 1 strictly, then the harmonic sequence 1 over n is going to be P summable. So the conclusion then is that if X and Y are elements of LP, so that means that if I take xk and raise it to the p and then to the power of 1 over p, I'll get something less than infinity. And the same for y. That's all this means. Then x plus y will also be in this space. So this is the one way to verify that if you add two vectors, or if you add two elements in LP, then their sum is an element in LP. So that's one part that you need to verify if you want to make sure that LP is a vector space. Okay, so this then shows that that must be the case. Do you see why? Need I say more? Yes? No? I guess it's yes. Okay. Because if I want to calculate, let's say, x plus y, and I take the p norm, it's very convenient to take its p power, because then that is what? That is the summation where k goes from 1 to infinity of xk plus yk raised to the power of p. Now what do I want to show about the sum? I want to show that the sum is what? That it is less than infinity. Okay, so one person is not completely lost. Okay, less than infinity. That's what I need to show. What do I know? I know that x, if I do this procedure to x, the sum will be less than infinity. And if I do the procedure for y, it will be less than infinity. Yes? So now look at the situation. That is a plus b. Each coordinate is an instance of a plus b raised to the power of p. And by the observation I just made above, this is less than or equal to the summation where this would be twice 2 to the power of p, and here I have x k to the power in absolute value to the power p plus y k to the power p. Okay? So from this we can now write it as two sums. So this is equal to twice p parentheses the summation for x k to the p plus the summation of y k to the p. And this, each of them is less than infinity, so then the sum is less than infinity. And that verifies this claim. Yep?
Why is there a 2 there?
There is a 2. You might try to find an easier inequality, but notice the p is not an integer necessarily, right? So it's not necessarily comfortable to use binomial theorem or anything of the sort. So what you do is this. So a plus b, it's a sum of two numbers, right? So instead of adding the two numbers, I want to just have one number here. One of them is the biggest number, because they are both bigger than or equal to 0. One of them is the biggest number, okay? So it's either twice a or twice b. So this maximum of ab is really, it's the either or. Either it's b or it is, either it's b or it is a. Right, so here, first of all, from here to here, right? Do you see? So the max ab just tells you select the biggest term. And why twice? Because I have the sum of them to the power p. So if instead of a and b, I just add the biggest term to itself, that will be twice the biggest term, and that's raised to the p, and I get something bigger. Do you follow? Guys, you follow? So the maximum is I. So basically, what I'm saying, this is either a plus a or twice a, or b plus b twice b, depending on what's the biggest thing. So max ab just tells me pick the biggest one of them. So that would be 2 times the maximum. So then I can take the power. It's now a product, so it's easily distributive. So it's 2 to the p times the maximum to the p. And now I want to get rid of the maximum, right? So then I say I can replace the maximum by either a or b again. So I first replace it by a, and I maybe I made a mistake. So then I replace it by b. So definitely the sum of a to the p and b to the p is bigger than the maximum to the power of p, because I either have b to the p or a to the p, and the sum is bigger. So that's just a simple play off on inequality. It's not very sensitive. It's just some sort of jumping higher and higher, just as long as I can find a bigger term. That's all I'm doing. Okay, so that implies, so using this little argument, I can quickly reason out that the sum of two elements in LP is again an element in LP. Okay? If you don't get it, again, okay, right? In our end, there is no point to it, right? In our end, there is no point to do this calculation. It's only when I have an infinite dimensional space that I have to worry about those inequalities. So, the worst inequalities are still ahead of us. So, our goal, so you understand the goal? Is that for any p that is bigger than 1 and less than infinity, you can even say including infinity, that this thing is a norm. And I'm using this very odd language. I'm saying the p norm is a norm, right? But the word p norm comes from the fact that it is a norm which we haven't verified. So that, I hope, is not confusing you. There are several things in this analysis where you have a name that seems to already suggest a property, but the name was then in some sense unfortunately given, maybe, or given later when the property was verified. So we will soon see something like we need to prove that an open ball is open. But that's because you think open is an adjective, but open ball is a noun in that case, right? Something is open. Okay? So similarly here, P norm is a norm. So how do we do that? So the biggest problem is the inequality. Triangle inequality. Okay, that's the biggest difficulty. If you know triangle inequality, everything else is pretty simple. So we already proved the triangle inequality using Cauchy-Schwarz and the Minkowski inequality for power 2. Okay, so we want to do that in general for any power p. So how to proceed? First, we have lemma, it's Young's inequality. And what this inequality is saying is the following. Given A bigger than 0 and B bigger than 0, and P bigger than or equal to 1 less than infinity, define Q by 1 over P plus 1 over Q is supposed to be equal to 1. So in the case I pick P equal to 1, first of all, this is, if P is equal to 1 or 2, the triangle inequality is trivial. But if P is equal to 1, Q will have to equal to infinity. Okay? So we have that 1 over P plus 1 over Q is equal to 1. You will see why. I'll try to explain why you have this property. And then what you have is the following. Then we have that A times B, the product of A and B, will be less than or equal to A to the power of P divided by P plus B to the power of Q divided by Q. Now notice, if you study probability, 1 over P plus 1 over Q is equal to 1. So this is a weighted average. Okay? So another way of seeing it is that A raised to the power of P times the probability 1 over P plus B to the Q times the probability 1 over Q. The two probabilities add up to 1. You have this inequality. Okay? There is the arithmetic geometric inequality that will follow as a special instance of inequality I'm presenting here. Okay, so one way to see why 1 over P plus 1 over Q must equal to 1 is those are weights or probability weights. I'll explain from the proof how that will also follow. So here we go. So for the proof I'm presenting, I'm reaching a little bit farther. I'm using integration, right, which I haven't fully justified in this course. But that's okay, right? If you believe integration works from calculus, you kind of get how this inequality will work in this proof. So what you do is draw yourself a graph, and in this graph, so the graph is going to be, let's say, of, so this is the y-axis, this is the x-axis. The graph is, on one hand, it is y equal to x to the power of p minus 1. Okay? If p is bigger than 1, the graph will be concave up. If p is if p minus 1 is bigger than 1, then the graph will go like this. But if p minus 1 is less than 1, the graph will go like square root. Okay? It doesn't matter, because you will see that if it goes one way as the parabola, or something similar to a parabola, it would be something similar to the square root if you take the inverse. Okay? So y to the x to the power p minus 1 on the positive x-axis has an inverse. And that inverse is just, you can see it already here. You just take you just take this. You take the same graph, and you label this as y to the power of 1 over p minus 1 is equal to x. And this will be 1 over p minus 1 will be the same as y to the power of q minus 1. Okay, so q minus 1 is given as 1 over p minus 1. And then you observe the following property. So let's say that anywhere on this graph I place A and B. So anywhere, right? Completely anywhere, this is going to be A, and this is going to be somewhere over here, let's say is B. Okay? Now observe what is A times B. A times B is going to be a rectangle. See? A times B is a rectangle that has one side at A, the other side at B, so it's this rectangle. You agree? That's A times B. Now let's see what happens on the other hand. So you see A times B is the area below the curve y equals x to the p. And then I have the area on the y-axis, but it extends a bit farther, right? Look at it. Extend the area on the y-axis a bit farther, and you get that the integrals from 0 to b plus the integral from 0 to a. So sorry, the integral from 0 to a of x to the p minus 1 plus the integral from 0 to b of y to the q minus 1 will be bigger than the square. So here is what I'm saying. So observe that the integral from 0 to a of x to the power of p minus 1 dx plus the integral from 0 to b y to the q minus 1 dy is bigger than or equal to a times b. The only way equality holds is if b is selected as, so if b is a to the power of p minus 1. So you see, if I selected this a, try to select one a and then vary the b. That's how you do it, right? Select an a and then vary the b. So here, the reason we have a bigger area is due to this region, right? So due to the integral from 0 to b over y. Now I can try to lower the b. I lower it, so at this point equality holds. You see, at exactly this point where y is equal to a to the power of p minus 1, I have exact equality. The rectangle is broken into two parts by the curve. Okay? Now if I lower b a little bit more, then a times b is going to be smaller because now the integral over the x-axis contributes a little more. Do you see that? I guess that means no.
Isn't this very similar to the arithmetic geometry?
It is very similar. It's more general.
With like the rectangles and the squares.
Right. It's related to the arithmetic geometric inequality. In fact, it implies it. So we have this observation. Just again, think about it. Okay. So you have this curve. And you have a times b. So fix a and then see if you can vary the b. Make b either higher or lower, and you see that this inequality must hold. Okay? If b is higher than y corresponding to this point, then the integral over the y-axis contributes too much. If b is lower, then the integral over the x-axis contributes too much. In any case, you see, equality only holds in the special case, again, where b is given as the y value of this point. Okay?
The one thing that is a little confusing, you said that 1 over y to the p minus 1 equals x is the inverse of y equals x?
Yes, 1 over, so y to the power of 1 over p minus 1 is the inverse function. Right? Is this confusing? So let's see what happens. So if I have y equals x squared, what's the inverse? You take the square root, so you have y to the 1/2. You just take 1 over that power will be the inverse. It will be the x. Okay? So in general, if I have if I have y equals to x to the power of p minus 1, I take the p minus 1 fruit on both sides, and that is written as y to the 1 over p minus 1.
I was just confused because I thought you wrote 1 over, in general, y to the p minus 1, not y to the 1 over p minus 1.
Yes, it's y to the.
Okay, that's why.
Right. Y to the, and then I just, you see, this is some number, and clearly a number can be written as q minus 1. So we have this. Now if I actually do the calculations, so what do I get? Do the calculation, this is just, this is going to be 1 over p x to the power of p, evaluated from 0 to a, plus 1 over q x to the q, evaluated from 0 to b, x, y to the q, right? Okay, we have this, and the solution then is a to the p over p plus b to the q over q, and that has to be bigger than or equal to a times p. So it's a very clever proof. Good? So here's something that maybe somebody would have asked immediately, or maybe you're just too tired of inequalities. Here's going to be your extra credit if you want to use it. Or just the following, right? So notice that what I'm going to claim is if you look at this proof, you will see that if I define q minus 1 as 1 over p minus 1, that is the same as saying 1 over p plus 1 over q equal to 1. Okay, that's exactly the same. You can just quickly calculate. You see it's the same. So true or false? So this is, you don't need to answer it now, you have to think about it, right? So if I have, let's say, a times b times c, they are positive numbers. So we have a, b, and c are non-negative numbers. A times b times c will be less than or equal to a to the p over p plus b to the q over q plus c to the r over r, where 1 over p plus 1 over q plus what? 1 over r is equal to 1. Okay? Because you can see you take weighted average. Is this true or false? And then consider this in general. In general, suppose that you have a1, a2, all the way to an. So you have that ak is bigger than or equal to 0. And you have p1, p2, etc., pn, each of them bigger than or equal to 1 less than infinity, such that 1 over p1 plus 1 over p2 plus 1 over pn equals to exactly 1. So do we have the inequality that a1, a2, an is less than or equal to a1 to the power of p1 over p1 plus a2 to the power of p2 divided by p2, etc., an to the power of pn divided by p sub n. Okay? So think, you think if this is true or not, can you come up with an argument? So you understand the idea of this proof, right? So it's very clever because it notices that the condition that 1 over p plus 1 over q is the same as the condition that q minus 1 times p minus 1 equals to 1. Okay? So I'll just put it here, just for you to pay attention. this is equivalent to requiring that p minus 1 times q minus 1 is equal to 1. The product of p minus 1 and q minus 1 is 1. Okay? You might even take this in the proof that was used as the condition. Notice that I used p minus 1 because I have this power rule in integration. So p minus 1, I can add 1 to it if I divide by p. Okay? And you might take it as even the primary reasoning, and then maybe observe that this is then also true. Okay? So this is going to be important. We're going to use this idea. We don't really need the general inequality for what follows, but this relates to, notice it's an average, right? So if they do also like the sums of probabilities, it equals 1, and this is a weighted average, and from this follows the arithmetic geometric inequality. If I'm not mistaken, I tend to forget their names. The arithmetic geometric inequality, I'll write it here. So that states that if you take the nth root of the product a1 through an, the nth root, that will be less than or equal to 1 over n summation a1 plus an. So if I called it by the wrong name, I tend to forget the names of inequalities. So all this is saying is that, you see, you take the product of the numbers, they are positive numbers, and you take the nth root. That implies that this quantity is less than the average. Okay? And why does it imply? I mean, you can see that what I said, p1, p2, pn, I set them all equal to n. So they would add up to 1. So in this case, the probabilities are equal. Okay? That's what's happening here. So this n is coming from those p's. Okay? Okay, so we need this because that is going to, we have now a generalized Cauchy-Schwarz inequality, better known as Hölder's inequality. So what this is, what Hölder's inequality is saying is the following. So suppose, so let p be a number bigger than or equal to 1 and less than infinity, and define q by 1 over p plus 1 over q equal to 1. Right? So 1 over p is going to be a number less than 1. In case p equals to 1, then q has to be picked to be infinity. Okay? So sometimes you allow, and then again, that's abuse of notation. In some ways, that's kind of a limit, right? So a little bit of abuse of notation. This infinity usually means growing without bound. Okay? But we can take it also to mean the extended real numbers. We can kind of say that this is also such a thing like a number for convenience. Okay? So 1 over p plus 1 over q has to equal to 1. Then if x is an element of L sub p, so that means that x is a sequence that's p summable, and y is an element of L sub q, absolute value of the inner product of x and y. So that's similar to Cauchy-Schwarz, as you can see, right? So we take the dot product or inner product of x and y. This will be less than or equal to the norm of x, the p norm of x times y in the q norm. Okay? So Cauchy-Schwarz is just the case p equals to q equals to 2. Okay? So 1 over 2 plus 1 over 2 will equal to 1. So Cauchy-Schwarz is just a particular instance of this inequality, which is Hölder. If you don't like the p's, just imagine that that it's just then you don't need to make sure that y is in LQ. Just imagine this is Rn. You can do it, I guess, for this course. So, why is this true? Proof? So, if I look at the summation, look at the summation where k starts at 1 and just goes only to n of, so that's the absolute value of xk times yk. So you see what I do is I start with the dot product. In the case where it's in P or in Q, I just will have to take the n and push it to infinity. But if you're just dealing with n-dimensional space, not just your regular dot product here, this is by regular triangle inequality of the absolute value. This is less than or equal to the summation k equal 1 to n of the absolute value of x sub k times the absolute value of y sub k. Good? So this is, you notice, we have a product a times b of two positive numbers. No negative for sure. Okay? Two numbers, and then what I can do is I can now apply Young's inequality. So this is now less than or equal. This is Young's inequality. That would be the summation where k equal 1 to n of this number to the power of p divided by p plus this number to the power of q divided by q.
Originally we were working
now, so we have this inequality, and I made a mistake. Small mistake, so let's correct it. I needed to divide it by the full norm in order for this to clearly follow. Okay? Sorry. I'll have to have more room here, so, 1 second. So here again, right? So what I'll have is, look at the summation where I divide by the full norm. So what I have here is, let me actually take the inner product of x divided by the pth norm of x, and y divided by the qth norm of y. We take the absolute value of that. It's a similar thing. Now the absolute value of this expression is equal to the summation. So we'll just take for fixed n. N. So let's say this is the inner product up to the nth term. Okay, so I don't really take the dot product everywhere, I stop at the nth term. Okay, that would be k equal to 1 all the way to n of x absolute, so of xk divided by the norm of x the p times yk divided by the norm yp. Okay? And what is this? What is this expression? Now I can move in the absolute value. If I use the triangle inequality of absolute value, this is less than or equal to this term. Times the absolute value of the y case over the y norm. yq. Very wonderful. You notice. Not everybody lost completely. At least you see that there are q's and p's. So we have this. Okay? And now here I apply Young's inequality. That would be, you see two numbers, so we have the summation is from k equal 1 to n. I take this number and raise it to the power p and divide by p. So that is, if I write it conveniently, that's 1 over p times xk to the power of p divided by the pth norm of x raised to the power p. Plus 1 over q by k to the power q divided by norm of y to the power q. Yep. Sorry guys, today is a technical lesson. This is not the last inequality, I think. Right, this is just a prelude. It's Hölder, and then you have one more, and then it's going to be a little easier. Then we can breathe again. So we have this. And now notice what this expression is. Look at it, right? So if I look at the first summation, so the first one is 1 over p times 1 over the norm of x to the p power multiplied by the sum of the xk to the power p plus 1 over q times 1 over the norm of y to the q power times the summation k equal 1 to n yk to the q.
Aren't they equal?
Equal? No, they're not, because this only sums to n. If in Rn they are equal, but in general, if we're doing it in LP and LQ, that's only part of the norm, right? So, okay, so you're wonderful. You notice that if we just are dealing with R to the n, then this is exactly the 1 over x to the p. But in general, this number is smaller. I mean, you see, this number is smaller than x to the p because we haven't added every term. We haven't added the full infinite vector. We only added part of it. Okay. So then this is less than or equal less than or equal to 1 over p times 1 over the norm of x to the power of p times the norm of x to the power of p. You just observe that this is like the p norm. I just don't say but raised to the p power, right? This summation is the p norm raised to the p power, and usually if n is not the full dimension, it's smaller sum. Yes, do you follow, guys? I see some of you.
Why did you on the first line
First line is here.
next to it?
Next to it is here.
Right. Why did you put y sub p instead of?
Yes, that's a mistake. Thank you for noticing. It's y sub q. It's just accidental. It should be y sub q. I don't know that y sub p makes sense.
So shouldn't you finish that statement as less than or equal to 1 over p times
Yes, it's not over. Then this is plus 1 over q times 1 over y sub q to the power of q times the q norm of y to the cube power. And those numbers, the product is smaller than 1. The product is smaller than 1 because the denominator here is bigger or equal. So this is less than or equal to 1 over p plus 1 over q, which then is equal to 1. So for every n, the absolute value of the dot product up to the nth coordinate is less than 1. Okay? So what's the conclusion? The conclusion is that in this dot product I can factor this constant, and I have that this is the same. The first line is the same as the dot product of x and y, or inner product of x and y, divided by the norm of x times the norm of y. This, we conclude, is less than or equal in absolute value, I should also mention, right? In absolute value, this is less than or equal to 1. And that is Hölder's inequality if I just multiply by those terms. So that implies that this is for every n. For every n implies this. Now I can take, because this one is fixed, I can change the n, and the inequality is always less than 1, so I then can take limit as n goes to infinity. You see, the idea is if you are dealing with Rn, then you don't need to worry about the subscript. And from this line to this line, from this line to this line, it's equality. So this is x, this is y, less than or equal to okay? Yes, please.
In the top line of the second part, how come?
It's all here.
Yeah. Why
Yep.
don't the pth norm x to the p power as the numerator and the denominator 1 over?
I should say equal. Less than or equal is correct. You can always say less than or equal, but if I am careful, I can just say that this is just equal.
They have to cancel out,
They have to cancel out, yes.
no matter what.
No matter what, so again, I didn't lie. If I say less than or equal, I was just not as precise as you, right? But this is better, yes, it's equal. Okay, so look at the argument once again. Okay, so what do? In general, if I take x in LP and y in LQ, I have infinitely many terms in my vector, right? So it doesn't add after, it doesn't have just 2 coordinates or 3 coordinates or million coordinates, it doesn't ever end. So what I do is I truncate, I take the truncated inner product, and that means let me just consider the inner product up to the nth term, okay? And see what I can estimate the first dot product of the first n terms. So then, the dot product of the first n terms gives you this number under inequality, so I can just distribute the absolute value. I'm just adding a bunch of numbers, and you have the regular inequality for absolute value. So we have this part, okay? Here, I have the first number is A, the second number is B. I use Young's inequality. And I have this quantity, okay? And then I see that I can factor out, this is just each of the coordinates are raised to the p power and are divided by the same element, right? The norm of x to the power of p, whatever that number might be, I can factor it out. So we have this. And we have, so you get it, you factor it out, and then you just observe that the summation is just part of the norm to the p power. Actually, either equal to it or less because we truncated it at n. So here we haven't added all the numbers. The more coordinates to the power of p that I add, the bigger is the sum. Okay? So from here to here we have an inequality. If it's ending with p, then this is also an equality. If n is the dimension of my vector, then this is equality. But if n is not the dimension of this vector, this will be an inequality. Okay? So we have those x's, they cancel out, and then we just use that 1 over p plus 1 over q is 1. And that implies then again all this line, now I can just look back in here, no matter what's n, this quantity is less than 1. This quantity is the same as what I wrote here. If you review dot product, you quickly see that I can factor out from the first coordinate and factor out from the second coordinate to get this expression. And now I can multiply back by x to the t, y to the q, and I get my Hölder inequality. Okay? One small thing to worry about, you can see that this doesn't work if the magnitude of x is equal to 0. But if magnitude of x equal to 0, this is trivial. Right? They are equalities. This is going to be, dot product is 0, and one of them is 0, so it's 0. Right? So if one of them is equal to 0, you don't need to do this procedure at all. It's always an equality. Yep.
I follow the proof, I don't get, what was the benefit of using n instead of...
The benefit is that I need a finite sum. Okay, so they're going to be again, right? Mathematicians, they like to generalize, and also this is just you will see if you study analysis onwards, you will see big LP spaces. They involve integration, the back measure integration, and you use essentially the same ideas because integration is very similar to an infinite sum. Okay, so those are just sequence spaces. And if you are dealing with infinity, this proof is just using that idea that an infinite sum is a limit of a finite sum. So you consider the sum up to the nth term, okay? And if you consider the sum up to the nth term, that would be an inequality. If the vector is finite, this would have been an equality. Okay? So. Not sure if you are satisfied with what I said, but well, if you're dealing with infinity, you have to worry that the quantity that I'm considering is a finite number because inequalities, they work for finite numbers. It's dangerous when you don't have a finite number. What it even means. Okay. Right. Well, so. That's why, right? If I have expressions like infinity times a number, it is a dangerous expression, what it means. In calculus, that meant a limit. If you consider the extended real numbers and you consider infinity as a number, you still have to be worried. What's infinity times 0? Does it make sense? Infinity times minus 3, what does it make sense? Okay? So if you consider the summation only up to the nth term, this entirely is working by thinking, it applies to the real numbers. You don't need to do it. So finally, Minkowski's inequality for the p norm. Last straw. By the way, is there a benefit in me going over it in class, or you prefer me just taking it and I move on? Let me know. Maybe, should I go over it, or just write it out and you have it in my notes? Go over it, yeah?
Are you ever going to ask us to prove it
Sure. I mean, again, I prefer asking other questions, but you should know the proof. Again, very difficult. If you came up with such a proof on your own, that would have been a major achievement. It's very difficult, non-intuitive argument. So Minkowski's inequality. And it says the following. So given p bigger than or equal to 1 and less than infinity, in fact you can include infinity, what you have is if x and y are elements of the LP space, then we have that the norm of x plus y sub p is less than or equal to the norm of x sub p plus the norm of y sub p. Okay, and I use the word norm very, how do you say it, inconsistently, because unless I have this inequality, I don't know that it's a norm. Okay, it just, I don't know what else to call it. Okay, so I'm saying that it's a norm because of this problem. So proof. So what you have is, first of all, you fix n. So what you have is that if I take x plus y sub p, well, let's actually start if I fix n, the proof will go like this. So if I take this quantity, k equal 1 to n of xk plus yk to the power p. Okay? This is like the pth norm, but I raised it to the power p and I truncated it to n. I haven't added all the terms of the series. So if you have that, well, this is equal to k1 n. This is xk plus yk to the power of p minus 1 times absolute value of xk plus yk. I just factored one term out.
So we're defining Q to be the same as before, right?
Yes, Q is defined the same. So we're going to define, so Q given by 1 over P plus 1 over Q equal to 1. So we have this statement, and here I can use the inequality on the absolute value. Less than or equal to the summation k equal 1 to n of xk plus yk to the power of p minus 1. I'll put it in parentheses. No. I want to skip so too many steps. So we have this and times xk in absolute value plus same sum times yk. Okay, so that's to the power of p minus 1. Right. So then I'm going to use triangle inequality. Now for the x and for the y, I'm going to use the p power, and for the xk plus yk, I'm going to use the q power. Okay, so this is less than or equal to, I'm going to use Hölder inequality. Okay, this is like a dot product, right? So by the Hölder inequality, this is less than or equal to the summation from k equal 1 to n of xk to the power p to the power 1 over p times this term so that would be q, so this term to the power of p minus 1 to the power of q all to the power of 1 over q plus I apply Hölder inequality again for this term, but now with y. How much time do I have? 5 minutes or more? 4. Oh, you really want to get out.
Using the
Okay, so I bothered writing it all up for you. I wanted to skip it and write the solution already, right? So now it's annoying. Now you can factor this term and that term, and then let's actually see the arithmetic. I'll put the arithmetic here. I'm going to simplify this expression. Look at it. This is q times p minus 1. So over here, I'm going to make the following observation. So if I take q times p minus 1, that's the same thing as q minus 1 plus 1 times p minus 1. Remember that this inequality 1 over p plus 1 over q equal 1 is the same as q minus 1 times p minus 1 equal to 1. So then if I distribute this, this becomes q minus 1 times p minus 1 plus p minus 1. Okay? Which means what I get is simply 1 plus p minus 1, which is just p. Okay, so I just get p here. So I can take the q and p minus 1 and I get p. And I can also see that 1 over q is equal to 1. And then I also see that 1 over q is equal to 1 minus 1 over p, which is the same as p minus 1 divided by p. So I'm going to substitute those expressions. I'm substituting those expressions, and I get the following. Okay, so this is less than or equal. I'm gonna change this, and that's going to be the p norm. So instead of the n, I'm going to push the n to infinity, and this is less than the p norm. So what I get is that the above term is the x to the p norm, and then here I have y to the p norm multiplied by this summation. Xk plus yk. According to this, p minus 1 times q is just to the power p. And all of it is raised to the power of p minus 1 divided by p. Okay? So what is this? This is less than or equal to the norm of x plus the norm of y. And if I now push n to infinity, this becomes the norm of x plus y, which we know is finite from one argument I had before, to the power of p minus 1. So this is times x plus y norm p, but raised to the power of p minus 1. So what do I get? We're done pretty much, right? So now I can replace this inequality. So what I get is by pushing n to infinity, notice there is no dependence on n. Whatever n was, this is a bigger quantity. So I can now push n to infinity, and the implication, here we're done. The implication is that if I take x plus y to the power p, p norm, that's going to be less than or equal to the p norm of x plus the p norm of y, all multiplied by x plus y to the p norm power p minus 1. I can now divide by this quantity. Divide by this quantity, and I get that x plus y, the p norm, I just had p power, this had p minus 1, so dividing only one power is left, is less than or equal to x sub p plus y sub p. Boom, we're done. Goodbye.